There we go. Excellent. Alrighty. Good morning, everyone. Happy Monday morning. It's April 27th. I hope you had a fantastic weekend, and I hope that you did well on the practice problems that were assigned for today. Because today, what I'd like to do is I'd like to just go through some more examples for you in preparation for the progress assessment that will be coming your way in just a little bit at the end of class. The first thing I want to do, though, and I understand that these lessons are being recorded and that may make people somewhat nervous to either participate or speak up in chat, but I did want to provide you the opportunity to give me some feedback on how this distance learning structure has gone for you. My logic, now that we're in it for the long haul, my logic has been to just try to provide you with as much information as possible in as clear of a way as possible. And so that's really just turned into doing 30-minute lectures, more or less, where I just show you examples, try to explain examples, record them, and upload them, because I think that would be, to the most of your benefit as you go forward to try the practice problems. That was my logic anyway. I know a lot of other teachers are doing some really fantastic things where it's like, hey, can we take 10 minutes to do a problem on our own and then hold it up to the camera, like everybody turns their webcam on, and then I go through your work and point out some mistakes and stuff like that. And I think that's a great idea. The reason that I haven't adopted that personally is because I think that takes up too much time to justify what you get out of it. Like, it's not worth spending a third of our time together when we only meet twice a week on trying to do one problem and getting some feedback, versus I think what I can do is provide you with a lot more of examples and clarity in 10 minutes of time if I'm just going through them with you, versus taking all that time to just go through an example and get feedback. However, that's just my thought process. I want to hear from you if you think that it's going well, these recorded video lessons plus the examples. Do you think that's going well for you? Or do you think you want to mix it up a little bit? Do you want to try one of those more creative things? I'd be happy to try to venture into that territory if you want. I want to give you that opportunity to provide feedback. Now, like I said, you can feel free to type it in the chat now if you want. Like I said, I know since we're recording and it's going to be uploaded, some people are like, oh, I don't really want to participate. That's fine. You're in front of the whole class. I get it. No big deal. If you want to send me an email, if you want to send me a Google Hangout message, if you want to stick around after class and just talk with me one-on-one, that's totally fine. I welcome that as well. So, but anything I can do to help you out more, that's what we're here for. Miss Mao and I are here for, is to help you. So if you are like, Mr. Giorgio, this just isn't working for me, this structure is very difficult to follow along with, then that's fine. I want to hear and I want to see if I can help you out in whatever way as possible. Okay? Other than that, though, if you, conversely, if you're like, hey, this sounds great and I really want to, I want to continue with this structure. It's really working for me well. One thing I want to point out is Miss Mao's notes, I think, have been exceedingly helpful. I think just giving you a little shout out, Miss Mao, I think your notes are really fantastic and a great supplement to what we've been doing and what we've been talking about. So that is a great resource that we have as well. I know Miss Mao has regularly scheduled office hours and all that type of stuff, so you can go ahead and see her during that time if you need some additional assistance. I'm around as well, that you can reach out to me if you need additional assistance. But again, I want to provide you the opportunity for feedback, such that if you're finding that it's not quite working out, then please just reach out and let me know. Okay? All right, without any further ado, let's go ahead and get started. So that takes care of feedback. One more thing I wanted to mention is your assessment. So per my email that I sent out to you, which hopefully you all received, it establishes a pretty consistent structure going forward for our class. One thing that is in that email is it details a graded assessment that will be coming your way very soon. In fact, at the end of today's class, it is scheduled to go out to you via email. It's our first graded assessment of the fourth quarter. It is due by Thursday night at midnight. It's 4 graphing problems, just like the ones we've done in class and just like more that I'm about to show you now. Like I said, it is due Thursday at midnight. The reason for the Thursday deadline is so that on Friday I can go through and grade it and give you feedback during that day on Friday. So if I made it due at the start of the next class, which would be like Wednesday, I don't think that's enough time. And then if I made it due the start of the following class, that's like a week's worth of time. And I feel like that's just lagging behind. So that's the reason for the Thursday night deadline. That being said, I believe that is more than a sufficient and reasonable amount of time to get an assessment like that done. That gives you all day today for the rest of the day. You have all day Tuesday, all day Wednesday, and all day Thursday. And I know you have additional classes and meetings during that day and stuff. I'm not trying to act like this is the only thing you have going on, but I do think that is a more than sufficient block of time so that I'm not going to be accepting any late assessments in the absence of extenuating circumstances. If you email me and you're like, Mrs. Giorgio, I have X, Y, and Z going on. Can I get it to you, at a different time? Fine. We can work those out on a case-by-case basis. I have no problem with that. But in general, there really shouldn't be a reason why going from Monday afternoon to Thursday at midnight, that should be plenty of time. That should be plenty of time. All right. Does anybody have any questions as far as that is concerned? You'll be getting it via email just like before. Take pictures, submit it just like before. I'll grade it and get it back to you. Feeling good about that? I take your silence as, yes, Mr. Giorgio, we are feeling great about that. Not just good. We are feeling great. We are feeling geared up and ready to go with Algebra 2. You can hear Sean in the chat. He's like, yes, yes, we are. Absolutely. It's Algebra 2 time. It's Algebra 2 time. All right, here we go. So what I'd like to do today is I'd like to just go through a lot of examples with you on how to graph all of these rational functions. We did kind of a day one introduction. Day two was sort of expanding upon that introduction and then doing a couple examples with you. Now today is really where I'd like to just do examples to show you how to graph these types of functions. And that will lead perfectly, in my opinion, into your graded assessment at the end of class today. So just a little quick recap. When I'm faced with any rational function in order to graph it, what I want to do first is identify my vertical asymptote and my end behavior asymptote. The vertical asymptote is found by finding the value for x that would result in dividing by 0. In our little example up here, you find that x equals 1 would be the vertical asymptote because 1 would be a big problem if you tried to plug that in for x. 1 minus 1 would be 0, and you can't divide by 0, right? So that's what creates that weirdness of the asymptote. To find the end behavior asymptote, it's a little more complicated. You compare the degrees of the numerator and denominator. If the degree of the denominator is larger, your end behavior asymptote is 0 from this piece plus the vertical shift. If the degrees are the same, you create a fraction out of your leading coefficients and then tack on your vertical shift. Okay? So in our example up here, you would see that the end behavior asymptote, let's see, the degree of the numerator is 0, the degree of the denominator is 1, therefore the degree of the denominator is larger, so your end behavior asymptote is 0 from this chunk plus the vertical shift of 3. So it would be 3. You can see right here. If, say, there were an x up here, say it were x divided by x minus 1, you would see the degree of the numerator and denominator would be the same. It would both be 1 because it's x to the first power. So you would do leading coefficient of 1 divided by leading coefficient of 1 plus 3 would make 4. All right, so that's how you find your end behavior asymptote. After you do that, you draw your asymptotes on the coordinate plane. You go ahead and test some points for x that you plug in. You want to plug in 2 values to the left and 2 values to the right of the vertical asymptote. So in our first example here, you saw that I plugged in 0 and -1. That's 2 to the left. And I plugged in 2 and 3. That's 2 to the right of wherever your vertical asymptote happens to be. Okay? We take those values, we plug them in for x, we get the y values, and we draw our curves approaching but not touching the asymptotes, because that's what asymptotes are. They're these boundaries that your function will approach infinitely but never touch. Okay? Does anybody have a question in general on that process at all? Feeling good about that? Hopefully? All right, so the last thing about that is the domain and the range. Keep in mind that your domain is all real numbers because the graph extends to the left forever and extends to the right forever, but it does skip over one particular value, and that particular value is 1, right? So it's really all real numbers except this value of 1, which is where your vertical asymptote is, because it goes everywhere to the left of that, everywhere to the right of that, but it never hits 1 itself. So that's why your domain is -infinity to 1 union 1 to infinity. Your range is a very similar idea. It's how far down does the graph go, how far up does the graph go. It goes down forever, it goes up forever, but it will never actually hit this value of 3. So it's like this little break or this little gap or jump right in the middle here where I go -infinity to 3 union 3 to infinity. So that's rational functions in a nutshell. With that 10-minute introduction out of the way, I now want to go ahead and just run through some examples with you to hopefully clarify everything on rational functions. If you do have any questions as we're going through these, please just interrupt me or type it in the chat and let me know, and I'll be happy to address it. That's what today is for. Today is for, let's see a couple more examples. Let's go through any questions if you have any questions, and hopefully we'll have a great rest of your Monday. All right, so starting with a problem like this. Ready? What if I asked you to sketch a graph of 3x divided by x plus 2 and then minus 1? Okay, the rational function has an x in the denominator, so we can go ahead and approach it just like any other. First things first, I'm going to try to find my vertical asymptote. Again, the vertical asymptote is caused by the divide by 0 case, where I would look here and I'd say, oh, well, what value would cause division by 0? It would be x equals negative 2, because negative 2 plus 2 would be 0, and I'd be dividing by 0 if I tried to plug in negative 2, which would be very bad. So our vertical asymptote is at x equals negative 2. Okay? Our end behavior asymptote, in order to find that, what I do is I compare the degree of the numerator and the degree of the denominator. The degree of the numerator, again, what power is x raised to? It's 1, x to the first. Degree of the denominator is also 1, so they have the same degree. Since they have the same degree, I'm going to make a fraction out of the leading coefficients and then tack on the vertical shift. We got 3 leading coefficient divided by 1 leading coefficient is 3, minus 1 is 2. So our end behavior asymptote is y is 2. Any questions as to how we got that vertical asymptote and that end behavior asymptote? If you're thinking of a question, I'm going to go ahead and sketch in my coordinate plane here. So we have our coordinate plane. I'm going to leave a lot of space on this side here because you can kind of see that's where our vertical asymptote and that's where our end behavior asymptote are. So we're going to be using that corner of the graph. No reason to waste paper, right? Let's draw in our vertical asymptote at negative 2. Our end behavior asymptote at 2. Right here. Okay? And now let's go ahead and test some points. What I do in order to test points is I'm just going to pick 2 values on the x-axis to the left and 2 values on the x-axis to the right of the vertical asymptote. So since my vertical asymptote is positioned at negative 2, I'm going to go ahead and plug in negative 3 and negative 4. So we'll go negative 4, negative 3, right in increasing order. And then I'll plug in negative 1 and 0. Just like that. Okay? Let's take these values, plug them in, and see what we get. If I take negative 4 and plug it in, again, sometimes when there's 2 plug-in spots, it's easier to actually just write it out. We get in the numerator 3 times negative 4 is negative 12. In the denominator, negative 4 plus 2 is negative 2, and then minus 1. Negative 12 divided by negative 2 is positive 6, minus 1 is positive 5. So I got a point at negative 4, comma 1, 2, 3, 4, 5. Right like that. So everybody see that? Next, I'm going to go ahead and plug in negative 3. Negative 3 goes in. In the numerator, I get negative 9. That's 3 times negative 3. In the denominator, I'm going to get negative 3 plus 2 is negative 1, and then minus 1. Negative 9 divided by negative 1 is positive 9, minus 1 is positive 8. So I get another point at 1, 2, 3, 4, 5, 6, 7, 8 right here. Draw my asymptotes up. And this actually is a great example of why it's helpful to draw in those asymptotes, because those are going to serve as guidelines for how to draw my curve. You could probably see it in your head right now. The curve is going to approach but not touch the asymptotes. Before I draw it in, though, I want to go ahead and just plot the other side. Negative 1 goes in. 3 times negative 1 in the numerator is negative 3. In the denominator, negative 1 plus 2 is 1, and then minus 1. I get negative 3 divided by 1 is negative 3, minus 1 is negative 4. So I got a point at negative 1, comma 1, 2, 3, 4 right there. Again, notice your asymptotes are going to guide that curve. And lastly, 0 goes in. 3 times 0 in the numerator is 0. 0 plus 2 is 2, minus 1. 0 divided by 2 is 0, minus 1 is negative 1. My last point's right there. See how these look to be symmetrical, by the way? You should always notice that form of symmetry, which is really, really nice around this point. Okay? And now, like I said before, I'm just going to go ahead and draw in my curves. Approaching, trying to do the best I can here, approaching but not touching, the asymptotes approaching but not touching the asymptotes, like that. Okay? Questions, comments, concerns as to how I constructed that graph at all? Any questions? Again, I think that's why you want to draw in the asymptotes, because it gives you those guidelines for how to draw your curves. They can't cross these lines, and by the way, none of your graphs should have curves that are crossing the asymptotes, because that's the whole point of the asymptote. It's like a wall. So I think that's why it's beneficial to draw them in. One common misconception that I want to clear up, this came up in my A1 class the other day. Actually came up after class. I kind of wish I mentioned it to them. When you draw in your asymptotes, right, what those are exactly what I've just said. They are guidelines for how to construct your curves once you plot your points. A common misconception that came up the other day was, hey, once I draw my asymptotes, does this become my new coordinate plane? In other words, like, is this now 0, 0, and this would be 1, 2, 3, 4? No. This is just a marker on your standard coordinate plane as to how to construct your curve. So this doesn't create a new graph or anything like that. They're just little guidelines to help you draw your curves. This is still your coordinate plane, so that point is still 0, 0. This doesn't become like a new 0, 0 or anything like that. I just want to make sure I clear that up. Last thing we have to do on this graph is talk about its domain and range. Again, the domain goes forever to the left, goes forever to the right, but it does not hit this value of -2. So your domain would be -infinity to -2, union -2 to infinity. And your range goes forever down, goes forever up, but doesn't hit 2, right? Do you see how it jumps over this value of 2? It goes everywhere below 2 and everywhere up 2, but not 2. So it would be -infinity up to 2 and union 2 up to infinity. Any questions about that? Hopefully not. Feeling great. All right, fantastic. Let's do another one. How about an example like this? What if I said f of x is equal to -2 over x minus 3, and then plus 4? Okay. How about a rational function kind of like that? Well, just like before, I'm going to find my vertical asymptote. I'm going to find my end behavior asymptote. The vertical asymptote here would be, looks like x equals 3, because what value would result in dividing by 0? It would be +3. 3 minus 3 would be 0, and then you'd be stuck, 100% stuck. There'd be nowhere to go from there, right? So your vertical asymptote is 3. Your end behavior asymptote, compare the degree of the top and the bottom. In this case, the degree of the denominator is larger, so your end behavior asymptote would be 0 from this chunk, plus the vertical shift of 4. It would be y equals 4. Okay? I'm now going to go ahead and sketch my graph. Again, if you have any questions, please feel free to ask. But I have try to do the best I can here. Notice I'm going to leave a lot of room on this side this time. My end behavior asymptote of 4 is right here. My vertical asymptote of 3 is right here. Now we're going to go ahead and test some points. So just like this. That wasn't the straightest of lines I've ever drawn, but that's all right. Since my vertical asymptote is located at x equals 3, I'm going to go ahead and plug in 1 and 2 from the left. See? 1 and 2 from the left, and 4 and 5 from the right. Because I want 2 points to the left and 2 points to the right of that vertical asymptote, just so I can get a nice, pretty picture. We take these values, we plug them in. Let's see what we're going to get. If 1 goes in, 1 minus 3 is -2. -2 divided by itself is 1, plus 4 is 5. So I got a point at 1, 1, 2, 3, 4, 5 right there. 2 goes in, 2 minus 3 is -1. -2 divided by -1 is +2, plus 4 is +6. Another point right there. Again, you could picture how the curve is going to look. That's why the asymptotes are helpful. You can picture it's going to look just like that. 4 goes in. 4 minus 3 is 1. -2 divided by 1 is -2, plus 4 is +2. Right there. 5 goes in. 5 minus 3 is 2. -2 divided by 2 is -1, plus 4 is 3. Again, you should be able to observe that symmetry even before you sketch your curves. You see that symmetrical structure taking place. So I'm going to go ahead and draw my curves. Approaching, but not touching. Approaching, but not touching the asymptotes. And that's what our function would look like. Okay? Domain and range are the last two things we need to do. Okay. My domain here is, again, it extends forever to the left, extends forever to the right, but does not hit this value of x equals 3. So you would say your domain is negative infinity to 3, union 3 to infinity. If you've noticed, it really just jumps over your vertical asymptote. That's exactly what happens with your domain, right? It just skips over this value that x cannot equal. And that's a great connection, because if you notice, vertical asymptote is written as x equals 3, meaning that you're saying 3 is the problematic x value. So there aren't any other problematic x values, so that's why your domain is written like this. Your range, it's kind of the same deal. You're saying y equals 4, that's the problematic y value. There aren't any other problems, though. It's only this one that causes a headache. So I can say my range is all real numbers except 4. Everything less than 4 or everything greater than 4. Just not 4 itself. Everything less than 4, everything bigger than 4. It just never hits 4. Any questions about that at all? Sean, that is excellent. He says, nope, which means we're going to move on to another example. Just going to keep on rolling for more examples, and more examples. Here we go. How about this one? This one I think is cool because it's deceptively simple. How about x divided by x plus 3? Something like that. Okay, let's give that one a shot. Vertical asymptote would be x equals negative 3. Negative 3 plus 3 causes the divide by 0 case, just like we've seen before, so that would be our vertical asymptote. Our end behavior asymptote here, I'm going to compare the degree of my numerator and my denominator. The degree of the numerator is 1, because it's x to the first power. The degree of the denominator is also 1, x to the first power. Therefore, they have the same degree. Since they have the same degree, we create a fraction of the leading coefficients and add on the vertical shift in order to find the end behavior asymptote. Here, our leading coefficient in the numerator is 1, divided by our leading coefficient in the denominator is also 1. So 1 divided by 1 is 1. There is no vertical shift, so I would just say our end behavior asymptote is 1. Okay. Again, just to summarize that, the degrees are the same. I take the leading coefficients and divide them by each other. 1 divided by 1 is 1. Okay. I'm going to go ahead and draw my graph now. Let's see. Negative 3 and 1. So I'm going to try to draw the coordinate plane so I can leave a lot of space over there. Something kind of like this. Should be good. Okay. I have my vertical asymptote at negative 3 right here. I have my end behavior asymptote at positive 1 right here. I can now go ahead and test some points. So let's see. My vertical asymptote is positioned at negative 3. So I'm going to go ahead and plug in negative 5, negative 4, negative 2, and negative 1. Do you see how that's two values to the left, two values to the right of negative 3? It's just counting. Negative 5, negative 4. We skip negative 3, negative 2, negative 1. Okay, great. These values go into the function. Again, when there's a plug-in on the top and on the bottom, when there's a variable positioned in the numerator and denominator, it's often easier to just kind of write it out so you don't get lost in your head. When there's only one, sometimes you can do it in your head really fast, but when there's more than one, it's a little trickier. So negative 5 goes in the numerator, we get just negative 5. In the denominator, negative 5 plus 3 is negative 2. Negative 5 divided by negative 2 is positive 2.5, or 5 halves, right? So I got my point at negative 5, comma 1, 2, and a half right there. Everybody sees how that works out? Negative 4 goes in. In the numerator, I get negative 4. In the denominator, I get negative 4 plus 3, which is negative 1. Negative 4 divided by negative 1 is positive 4. So I got negative 4, comma 4. 1, 2, 3, 4. Okay. Negative 2 goes in. In the numerator, I got negative 2. In the denominator, negative 2 plus 3 is 1. So we got negative 2 divided by 1, which is just negative 2. So I got a point at negative 2, comma negative 2 down here. And last but most certainly not least, negative 1 goes in. In the numerator, we just get negative 1 by itself. In the denominator, negative 1 plus 3 is 2. So that comes out to be negative 1/2, negative 0.5. Right about there. And then let's see. We're going to draw our curves approaching but not touching. the asymptotes. Approaching but not touching the asymptotes, just like that. Okay? Last thing we need to do is domain and range. The domain of the function is all real numbers except -3, everything less than -3, negative infinity to -3, or everything greater than -3. The range is everything less than 1, which is our end behavior asymptote, or everything greater than 1. Okay? Alrighty. Does anybody have a question, comment, or concern on that one? We've done 3 examples now. Feeling good on this? Hopefully. Making sense? Logical, following all the steps, following all my variable plugins and substitutions there. All right. I don't think we have enough time to go through another full example, but because we've gone a little over in the past, so I'll go a little under today. But what we have done, or what I want to show you rather, before I recap, what I want to show you is actually the example that I had in store, just to point it out to you. I had the example of 2 over x minus 4 was my next example that I wanted to present to you. And the reason I just want to show you this quickly is to ask you, what would be the vertical asymptote of that function? Well, you may look here and you might be like, well, it's just an x. Like, what is it supposed to be? Here, when it's x plus 3, it's -3. When in the previous examples, when we saw it's like x plus 2, it's just -2. And when it's x minus 3, it's +3. What if it's just x by itself? Well, if it's just x by itself, it's actually the simplest case. What value, if I plugged it in for x, would result in dividing by 0? Well, it would be 0, right? Your vertical asymptote would be 0 itself. It would be the y-axis, okay? Which is where all the x coordinates are 0. And your end behavior asymptote here would be -4. And the reason it would be -4 is because the degree of the denominator is larger than the degree of the numerator. The end behavior asymptote 0 from this piece, -4, so -4. Okay? But hopefully you understand, just seeing an x by itself results in that vertical asymptote of x equals 0. That's a very important point, so I just want to make sure that I delivered that to you today. Okay, quick recap. So what we did today is a couple examples. I went through 3 examples with you today. This is one where the degrees were the same, so that resulted in that end behavior asymptote. This is one where the degree of the denominator was larger, and then this is one, again, where the degrees were the same, so that's how we got our end behavior asymptote. This one had a couple fractions thrown in. These had just integers. Okay? Does anybody have any questions, comments, or concerns as we wrap up today on any of the problems that we've done? Nothing. All right. Well, if you do have any questions and you just maybe don't want to say them in front of the whole class or want to approach one of us individually, I want to again remind you that Miss Mao does have regularly scheduled office hours that you can attend for some Algebra 2 CP extra help. These videos are posted on YouTube, so you can go ahead and watch them back if you need to watch them back. And in about 5 minutes from now, I have it scheduled to go out at 11:15. You should receive an email in your inbox for your progress assessment that is required to be done and sent back to me by Thursday night. So that's Thursday at midnight. Make sure I get that back in my inbox. I'll try to send you a reminder, probably maybe on Wednesday or Thursday, just to get that to me. So that way I can grade it on Friday, get it back to you, and we'll go from there. All right. Next time I see you will be at Wednesday. Wednesday, we're going to take a look at some more complicated versions of these rational functions. There's one other twist that we're going to throw in there. It's not too bad. I promise you'll be able to do it. Don't get too freaked out and nervous about it, but you'll be able to handle it. We'll throw in one more little twist. We'll talk about that for the next 2 class periods. We'll have another graded assessment, and then we're going to move into solving equations. Thank you so much for your attention and focus today. I appreciate it. I hope you have a fantastic rest of your Monday, and let us know if you have any questions or concerns. All right. Thanks again.